Thermal imagery-based inspections refer to the process of collecting and analyzing infrared images of photovoltaic systems. Today, this has become a widely accepted best practice, and infrared inspections of PV plants are most commonly carried out using aerial methods. By analyzing abnormal temperature variations and thermal patterns across the inspected PV arrays, it is possible to locate and diagnose almost any critical defect or failure, even those that cause only minor performance losses. At the same time, this approach allows for the early detection of hot spots and potential fire risks. These infrared scans can be used either alongside manual electrical testing or, in some cases, as an alternative to it. At present, aerial thermal imaging of PV plants can be performed using either manned survey-type aircraft or unmanned aerial vehicles, such as drones. The overall diagnostic quality of these inspections depends heavily on several factors, including the type and performance of the imaging sensors, the measurement conditions during data acquisition, and the post-processing systems and algorithms that are applied afterward. The collected imagery must be processed using validated routines in order to correctly identify the thermal signatures associated with PV failures and defects, as well as their exact physical location in the field. This failure data, which appears as distinct thermal patterns, typically has very high spatial resolution, ranging from system level down to individual cell level details. Once properly labeled, this information enables maintenance engineers and field technicians to quickly diagnose, classify, and address PV faults, as well as identify their root causes. When applied correctly, aerial infrared and visual imaging is therefore a very powerful diagnostic tool. However, the use of appropriate post-processing methods and image data analytics is essential in order to accurately localize, diagnose, and classify the full range of PV failure modes, and, where possible, to quantify them in terms of associated power losses. In many cases, it is also recommended to cross-validate the aerial inspection results with ground-based data and additional measurements, such as IEV curve tracing or electroluminescence imaging. This helps ensure proper root cause analysis, reduces the number of false positives, and supports better decision-making when planning corrective actions. Today, there are many suppliers offering aerial infrared and visual imaging services. Many of these providers go beyond simple inspections and also deliver full PV diagnostic solutions. These turnkey aerial infrared inspection services typically include AI-based data analytics, automated fault diagnostics, detailed reporting, and consulting services, such as recommendations for corrective maintenance actions for PV asset owners and maintenance teams. Within the broader context of PV operation and maintenance, these services are used not only for routine inspections as part of preventive maintenance, but also for reactive troubleshooting during corrective maintenance, as well as for commissioning activities and asset transfer processes. Leading providers of aerial PV inspections benefit from having access to very large and steadily growing inspection portfolios, already reaching the gigawatt scale. This allows them to compare underperformance issues and anomalies across many PV plants, using extensive fault libraries together with proprietary image analysis and IR and RGB mapping software. As a result, these services can detect a wide range of problems, from large-scale string, combiner, or array outages to more localized issues at the module, submodule, or even cell level. These include subtle defects such as potential-induced degradation, electrical mismatches, and associated hot spots. Most service providers also emphasize the fast return on investment of aerial inspections. This is mainly due to a reduction in preventive operation and maintenance costs of more than 10% compared to manual or ground-based inspections, as well as the recovery of about 1 to 2% of lost PV power capacity. That said, the equipment and inspection approaches vary across providers. While many rely on drone-based infrared imaging, some companies use infrared cameras mounted on aircraft. These systems can fly at higher altitudes and speeds, enabling very high inspection rates, up to around 100 megawatts per hour, which is several times faster than drone-based methods. However, this approach comes with a trade-off, as the reduced spatial resolution can make it difficult to reliably detect failures at the submodule or cell level.